Well, it's 12 noon. Thanks for coming back on time. I got page 20 up here. There was a request for another page as well. Here's page 20. And then somebody asked for the first page. I will definitely get that. So remind me at the beginning of the next break. I'm assuming you're meaning the first page of the entire sequence of notes that I've done today. And yeah, that's no problem. We'll get that done. And any other pages too. But as far as where we left off, we had just gotten to this page. And yes, I did do some lecture before I turned on my sound, but now I will restart. I put page 20 up there. I will put any other pages you want up, either at the beginning of the next break or after lectures. For now, let's get back to new material, and it is noon, and I do want to use our time effectively. So let's pick up with the lecture notes with what is the molar mass of ethanol. Ethanol, so I've given you ethanol with this, what's called a structural formula that breaks it up into parts of the molecule. We're not expected to know anything about that yet, but sometimes we will see this. And when we're doing our molar masses, the key thing is to make sure you count up all the carbons. And there are 2 carbons in this molecule. There are 3 plus 2 plus 1, or 6 H's, and 1 oxygen. And so molar mass means use the numbers on the periodic table under each element's chemical symbol. So it's 2 times 12.01 grams per mole for carbon, 6 times 1.008 grams per mole hydrogen, and 1 times 16.00 grams per mole oxygen. And if we add those up, 2 times 12.01 plus 6 times 1.008 plus 16, I get 46 to 2 decimal places, 46.07 grams per mole, and you can list it as CH3, CH2, OH. Okay. Now we will work the next problem. The next problem says how many hydrogen atoms are in 32.3 grams of ethanol. You will see this type of question on the homework, so let's definitely do it. We have our given, which is the number in our problem statement. And, ethanol. You can write the formula, you can write the name. You just need something to designate what it is. And so I'm going to write CH3, CH2OH. You could also write C2H6O, just something that designates what the formula is. And I'm going to make a long, what I call picket fence, because we're going to have a couple of unit conversions here. The first conversion I'm going to do is going to use the molar mass. Molar mass is 46.07 grams of ethanol. Per 1 mole. Like so. And there's a couple different ways to do this. I'm going to then answer the question right here is of in 1 mole of ethanol, how many moles of hydrogen are there? And what I would suggest to you is if that I have 1 mole of ethanol, well, let's backtrack. If I have 1 molecule of ethanol, there were 6 hydrogens, or 6 hydrogen atoms. If I have 1 mole of ethanol, you count them up and you get 6, and there will be 6 moles of hydrogen. So the 6 is just done by adding up 6, the number of hydrogens in the compounds. And then now that I have moles of hydrogen, in 1 mole of anything, there are 6.022 times 10 to the 23rd of that thing. And in this particular case, since H is an atom, we will do atoms of hydrogen. So now we have 3 unit conversion factors. It's starting to look a little bit more like a picket fence or a railroad tracks. Again, there are lots of ways to organize these unit conversion factors. This is just one. I'm going to push things up a little bit. And then we have 32.3. Then we are dividing by 46.07. Then we are multiplying times 6. And then we are multiplying times 6.022, exponent button, 23rd. And I get 2.53. Where is that? Times 10 to the 24th atoms of hydrogen. So there you go. All right, back on screen there. So it's a long problem, and again, step by step, we will practice. We will do this in lecture. We will practice it in homework. This is a companion problem because it's very similar to the last one we did, except different compounds. Calcium chloride here.
Excuse me, sir.
Question, yes?
Can we please go back to the other page before the CP question?
So this page?
Yes, correct. Okay, thank you.
Sure. Then we have companion problem. Now, there's a couple more types of calculations we need to learn in this lecture outline. The next one is percentage composition by mass. And there's at least 3 different ways to refer to percentage composition by mass. It's percent by mass, percent m/m, which is mass divided by mass, or percent W divided by W, which is weight divided by weight. Almost everything we do in this class is mass. The unit of mass is grams, so we've been using masses all along. But sometimes, especially in older things, you'll find W divided by W as well, and sometimes in the medical field as well. Now, the first question we want to tackle is, what is the mass percent carbon? And so mass percent carbon will be percent carbon mass by mass. And I'll give you the formula. So it's going to be molar mass of carbon and I've put molar mass of carbon in parentheses, and then times number of carbons. So that's just a little scribble where I made a mistake. And then you're going to divide that by the molar mass of the compound. And the compound is C6H5COOH, so molar mass of the compound, times 100%. That's the formula. Now let's apply it. And I'm going to move my equal sign over a bit to make sure I have room. The molar mass of carbon, straight off the periodic table, 12.01 grams per mole carbon. The number of carbons in this compound, I see 6. I see one more, so 7. And that's going to be divided by the molar mass of the entire compound. So we have 7 carbons, 6 hydrogens, and 2 oxygens. And we've demonstrated probably 3 or 4 different times how to do the molar mass. So what I'd like to do is, I'm just going to do it on my calculator now. And so I have 7 carbons, which is the same as the first part, but then I'm going to add 6 hydrogens times 1.08 plus 2 oxygens at 16 each, and I get 122.118. I will go to 122.12. And then writing out the rest of the formula. Now I'm ready to do my math. It's numbers on the top divided by numbers on the bottom times 100. And I get 68.84 percent carbon mass by mass. And that is to the correct number of sig figs, and I will always accept 3 sig figs. So either of these answers is fine. Excuse me. Practice, you can do the same thing again except for iron. And again, the answers for the companion problems are posted inside Blackboard. Now let's talk about Cheerios for a minute. I had Cheerios for breakfast yesterday, and they're a perennial favorite of mine and my daughter's in our house. And I was looking for the fact that for a problem where you could calculate using nutritional labels what the percent of a certain thing is. And it turns out, I don't know if you've ever seen this, there's regular Cheerios, and for a short time there was something called Cheerios Protein. And Cheerios Protein, the way it was being sold was that it had more protein, that it was a good source of protein, let's say. And so when keto diets and that other one, the one where you don't eat any carbs, I mean, Cheerios are a large portion of carbohydrates. So they wanted to seem like they had protein in them. Paleo, yes. No, and the other one was the Atkins diet, I think. Anyway, there's a number of these. Anyway, Cheerios is like, well, we have protein too. So they put out this product called Cheerios Protein, and you can't buy it anymore. But here's the nutrition label for it. And in a serving size of 1 1/4 cup or 55 grams, and I'm going to draw a line here because this is the data for the Cheerios. In Cheerios Protein. In 55 gram serving, there are 7 grams of protein. Okay? And then this is actually a label from Cheerios where I took a picture of the Cheerios in my house, and you can see that it's only got 5 grams of protein. So sure, Cheerios Protein has more protein than this. However, they were sneaky. The serving size was 39 grams. So in 39 grams, there were 5 grams of protein. And the question we're going to ask is, which has a higher mass percentage protein? And so we're going to do the same type of calculation. So it's going to be percent protein, mass by mass, is this time going to be grams of protein divided by grams of sample times 100%. And again, this is for regular old Cheerios that I had for breakfast yesterday. I get 5 grams protein divided by 39 grams of sample times 100%. And if I do that math, 5 divided by 39 times 100, I get 12.8. Percent protein mass by mass. Now let's do it for Cheerios protein. For Cheerios protein, so it's the same thing, but now we have 7 grams of protein and 55 grams of sample. And when I work this out, 7 divided by 55 times 100, I get 12.7% protein mass by mass. And so it turns out that regular Cheerios and quote unquote Cheerios protein had the same amount of protein. The only difference was that if you eat more grams of it, you get more grams of protein. Of course, you get more grams of everything else as well. And as far when I looked online, and I didn't verify this with Snopes, but it seemed like it could have been true, so therefore I went with it. No, I think it was. So Cheerios was sued, or General Mills was sued for false advertising, or misleading advertising, certainly, because it's really the same thing. Anyway, what I love about chemistry and what I love about science in general is it gives us the tools to evaluate people's claims, and we don't have to accept things just as they're presented. Anyway, and when you do the calculations, you can run the numbers and be like, well, I'm just going to eat regular Cheerios, or, what a scam, or what an attempted scam anyway. It's the same thing. I wonder if they charged more too. But anyway, so question, how can we determine CP problems or companion problems? So companion problems, I always label them. So on the previous page, I labeled this one as a CP companion problem, and we worked through this one. And in case you were not here earlier or missed that part, so your lecture outlines, when you turn them in, have to have all of the stuff I do. You do not have to do the companion problems when you turn them in, and you'll still get full credit. If you do the companion problems, I think that's a wise choice to get good practice in, but you do not have to do them. So hopefully that answered your question. Okay. All right. So, and you can definitely not buy Cheerios protein anymore. I've looked. Question, when should we be writing in scientific notation for our answers, specifically decimal numbers? Great question. If you look at some of the calculations that I've done, you'll see that so first off, I only use scientific notation when there's lots of zeros, meaning it's either a very large or a very small number. Like a number like 0.00642, I typically write with the zeros. So the answer to your question was, you can always write in scientific notation, and you can always write in regular numbers if you want. Like, I don't have a rule about it. The only thought that I would put into it is whatever's easiest for you. So this number for me is easier to write not in scientific notation. In fact, sometimes my calculator starts spitting out numbers in scientific notation, and I actually read the manual to figure out how to get it to go back to regular numbers. Unless it's like 6.3 exponent 14 minus, like then it'll keep it in scientific notation, just because there's not enough zeros in there. But hopefully that answers your question. Like you can use either kind of number whenever you want in this class. I don't have a strong preference or any preference. Okay, so here's another example of a problem that we can solve using percent composition. It says the liquid in an intravenous or IV bag is 0.9% sodium chloride. That's what's considered isotonic, meaning the same type of concentration of ions as blood. How many grams of sodium chloride are there in a 1.00 liter bag of this solution? Assume that the density of the solution is 1.00 grams per milliliter, the same as water. So this is a percent by mass problem, and what I do when I'm stuck on a problem is I see this 0.9% sodium chloride, and I see that I'm being asked for grams of sodium chloride. So I'm going to write out the formula for percent sodium chloride. And it goes like this: 0.9% sodium chloride, mass by mass, equals blank grams of sodium chloride per blank grams of sample times 100%. And I may not know what the answers are, and I'm definitely showing my process here, but in chemistry, whenever you don't know how to solve a problem, write something that you do know and see if that helps. That's like my rule of thumb anyway. So let's see. And I have a number here, and it means that if I can find one of these numbers, I can find the other one. And since I'm looking for grams of sodium chloride, I'm guessing that I'm not going to be able to find that in this problem statement. But I do see this 1 liter bag of the solution, so that's sort of our sample size. .00 liters of solution is our sample. And it also tells us that the density is 1.00 grams per milliliter. So if I can turn these liters into milliliters, then I can turn the milliliters into grams. Now, 1 liter, well, it'll self-convert itself, but 1 liter, if you remember, is 1,000 milliliters, or 1 milliliter equals 1 times 10 to the minus 3 liters. However you do it, this is 1,000 milliliters. And for the density of the solution is 1.00 gram per milliliter. And so this is the density. And I get 1,000 grams. And I can put my 1,000 grams in here. Oop, I wrote my grams twice accidentally. So since, and I'll cross out this one so there's only one. So the key takeaway for this one is, if you're not exactly sure what to do, start writing down some formulas you do know, because oftentimes if you do, you can then figure out what you do need. And now the next thing I want to talk about is how to do the math for this. So the math for this, I would do it as a cross multiplication problem. And so I would put this over 1, and then 0.9, so then I'd cross multiply. And if I cross multiply, it's going to be 0.9 times 1,000. So that's the top and the bottom on the other side. Equals to 1 times x times 100. So, and this is the cross multiplication. Is 0.9 times 1,000 equals 1 times x times 100. And once you've got this statement, then you can go ahead and solve it. So to get x by itself, divide through both sides by 100. And x equals, let's see, the hundreds cancel. 1 is just 1. So your answer is 0.9 times 1,000 divided by 100. So I get x equals 9, and that 9 is grams of sodium chloride. And I'm going to go ahead and box that just so I can tell that the answers, that's my final answer for this problem. And you don't have to box it. Normally I can find the final answer, but if it helps you stay organized and know that you've got the final answer, then great. Any questions about that? Okay. Well, then let's keep going. Let's see, time-wise, we've been going for 27 minutes. Let's go a little bit longer. So we got 1, 2, let's at least get one more page done. All right, so the reason one of the many reasons we just did percent by mass, is that it's useful when thinking about a lot of things, especially in the medical field like we just did. But in our class, it's going to allow us to solve what are called empirical formula problems. And the empirical formula, let's just discuss what that is. The empirical formula of molecules, and these are going to be with covalent bonds, as we will see. The definition of it is the formula with the smallest whole numbers possible. The formula with the smallest whole numbers possible. So, for example, glucose has a molecular formula of C6H12O6, and we can see that all these numbers can be divided by 6 to get, and that's the biggest thing it can be divided by. So we'll divide all of those by 6. And we'll be left with C1H2O1. And that's, so what's this? Its empirical formula is C1H2O1. And you don't need the ones. So the only reason to have the ones be there is just so you know what the number is. But you can also write CH2O. And hopefully that makes sense, because numbers are often placeholders. One numbers are often placeholders to let you know that a number's there. Now, many compounds with different molecular formulas can have the same empirical formula. I'm showing 4 of them right here, and you don't have to know the names. The names are only here so that you can tell these are different compounds. But you can see that both of the numbers C3H6 can be divided by 3. C4H8 can be divided by 4, etc., etc. So all of these compounds have the same empirical formula. And then once you have the empirical formula, the way to get from empirical formula to molecular formula use the molar mass. And what I mean by that is, if you get the empirical formula and you're given the molar mass, that's when you can find the molecular formula. If you do not have the molecular formula, you probably can't find the molecular formula, as we'll see. So there's one more wrinkle here, and I just want to mention this. Even compounds with the same molecular formula can have different structures. These are called structural, and here's where there's a typo. These are called structural isomers. So please correct that. For example, C2H6O, there are at least two, and I think more, but at least two that have the same molecules with the same molecular formula. And I'm going to draw them out. And again, we're not supposed to be able to do this yet, but I just want to show you what isomers are. So you've got the idea of what an isomer is in the back of your head. So this is one isomer of C2H6O. You can see there are 2 carbons, there are 6 hydrogens, and there's 1 oxygen. And the oxygen has 2 pairs of dots, which we will see to be electron pairs later on. But if you rearrange the same atoms, so you still have C2H6O, you can get a different arrangement. So these two are isomers. And again, so let's put that in parentheses for now. Parentheses means something to think about, but not necessary to remember, or let's say not necessary to memorize how to do them until later in the course. When it's later in the course, then I will tell you about isomers again. All right, did I say we were going to stop? Yes, we're going to stop there, and then we're going to come back and do an empirical formula problem and continue the notes. So it is 33, 32 on my computer. So we're going to go till 12. I'm going to restart at 12:40. And in the meantime, I'm going to put up the first page. If I can find it. And I'll put up the first page. Are there any questions before I go on break?